Golden Iris Productions presents Why Quantum Theory and Gravity Disagree, a story from the Big Bang.
What if mass is not concentrated energy at all, but the cold, slow shadow left behind as energy drains into the vacuum? The beginning. In the earliest moments after the Big Bang, the universe was not made of particles or forces. It was an almost perfectly uniform plasma, a dense, searing sea of energy. There were no atoms, no light traveling freely through space, and no gravity as we understand it today. Yet from this simplicity, all structure would emerge. The central problem. Modern physics explains the universe using two powerful but incompatible frameworks. Quantum field theory governs particles and energy at the smallest scales. General relativity governs gravity, space, and time at the largest scales. Both work exceptionally well, yet they fundamentally disagree about the nature of reality. Two incompatible assumptions. Quantum theory treats mass as localized bundles of energy embedded in an otherwise quiet vacuum. General relativity, on the other hand, reveals mass as something that slows time and reshapes space-time itself, implying that the vacuum is active and structured. These opposing assumptions guarantee conflict. A conflict in physics. The standard view holds that mass is concentrated energy and the vacuum is empty and inert. This work, as well as modern cosmology, proposes the opposite. Mass is a cooled condensation of an early energetic plasma, existing in a low-energy, slow-time state. The vacuum retains the higher energy condition, stretched and preserved as the universe expands. Energy did not disappear. As particles condensed out of the primordial plasma, energy was not destroyed, it was expelled into the universe. Matter became cold and slow, the vacuum became vast and energetic. The darkness of space is not emptiness, it is stored energy. The time-energy inversion. Where mass forms, energy has been shed and time runs slowly. This is not radiated or electromagnetic energy, but energy withdrawn from motion. Where matter is absent, energy remains distributed through the vacuum, not as heat or light, but as dark energy, and time runs faster. This inversion lies at the heart of gravity and cosmic expansion. From plasma to particles. As the universe expanded and cooled, the uniform plasma underwent a phase transition. Protons and electrons condensed out of the energy field, much like droplets forming in cooling vapor. Their energy was not removed completely, but confined within them. Tiny fluctuations broke perfect uniformity, seeding the first structure. Recombination. In the early universe, energetic photons prevented electrons and protons from binding. As cooling continued, electrons finally combined with protons to form stable hydrogen atoms. This moment, known as recombination, transformed the universe from opaque to transparent.
The birth of light. With electrons bound into atoms, photons were no longer endlessly scattered. Light was released to travel freely through space. This ancient light still fills the universe today as the cosmic microwave background. Motion without collapse. Electrons did not lose their motion when captured. They occupied stable orbits governed by momentum and spin. Photons were absorbed and re-emitted as electrons shifted states, a continuous dance of matter and light mediated by the vacuum itself.
Atoms begin to gather.
hydrogen atoms began to cluster. Small clouds grew into larger ones, deepening the vacuum differential. Matter fell inward along this gradient, while energy radiated outward, redistributed, not consumed.
The creation of gravity. As clouds of hydrogen grew denser, pressure and temperature rose. Matter began to move inward, but not because of a classical force. Instead, the energy between particles was lower than the surrounding vacuum, creating a natural imbalance that drew matter together. Gravity arose as matter responded to this energy differential, moving toward lower energy regions while retaining its intrinsic motion.
The first stars ignite. When core temperatures within these clouds of hydrogen became extreme, nuclear fusion began. Hydrogen fused into helium, releasing immense energy as light and heat. The first stars ignited. Their inward tendency to collapse became balanced by the outward pressure of radiation from fusion, creating stable, shining systems.
Neutron formation and early isotopes. In the cores of dense hydrogen clouds and early stars, extreme pressure and temperature forced electrons and protons to combine, forming neutrons. These neutrons enabled the first isotopes, deuterium with 1 proton and 1 neutron, and tritium with 1 proton and 2 neutrons. With these steps, the universe began to form elements beyond simple hydrogen. Stars as cosmic foundries. With successive fusion in stellar cores, helium atoms were created from hydrogen and the first isotopes. Stars became cosmic foundries, transforming simple hydrogen into helium and heavier nuclei, producing the building blocks of matter, planets, chemistry, and life itself.
Gravity emerges from the vacuum. Electrons in newly formed atoms remained in stable orbits, never spiraling into protons. Atoms and clouds of matter did not collapse despite gathering together. Gravity arose naturally from a differential. Matter moved towards regions of lower energy relative to the surrounding energetic vacuum, without losing its intrinsic motion. Newtonian gravity. Newton's equations describe how objects respond to this gradient. G equals G times m over r squared. V equals the square root of 2gm over r. G equals v squared over 2r. They describe motion, not the source of attraction. Time hidden in the math. When relativistic time dilation is included, the deeper meaning appears. Mass slows time. The vacuum preserves faster temporal flow. Gravity, motion, and escape velocity are all expressions of an energy gradient, which is also a time gradient. Why the theories disagree. Quantum theory assigns energy to particles and silence to the vacuum. Relativity assigns energy and structure to spacetime itself. They cannot agree because they place energy on opposite sides of the universe.
The conceptual conflict. The conflict between quantum theory and gravity is not mathematical, but conceptual. Quantum mechanics and quantum field theory work beautifully mathematically, yet their assumptions about mass and the vacuum are upside down. Mass is not composed of concentrated energy, it is a condensate of confined energy. The vacuum is not empty, but energetic and structured. Gravity as a gradient. When mass is understood as a low-energy condensation within an energetic vacuum, gravity emerges naturally. It is not a force acting between objects, but motion along an energy differential. In this view, the universe becomes conceptually whole, uniting quantum mechanics, relativity, and cosmology.
Summary of our journey. We have travelled from the blazing plasma of the Big Bang to the first atoms, neutrons, and stars. We've seen how matter emerged, how light began to travel freely, and how gravity arose from the subtle energy differentials of the vacuum. This journey shows that the universe is not just a collection of particles and forces, but a story of energy, structure, and motion intertwined. The Great Conflict. Along the way, we've seen why quantum mechanics and general relativity disagree. One views mass as bundled energy in a quiet vacuum. The other sees mass as slow-time condensation within a structured, energetic vacuum. Our quest for understanding requires us to confront these conceptual differences, to see beyond equations, and ask, what is really happening in the fabric of the cosmos?
The adventure continues. The story of the universe is far from over. Every atom, every photon, every star holds clues to the hidden principles that shape reality. Our next journey will explore the next layer of this cosmic mystery, from gravity and vacuum to the profound questions of time, space, and the quantum fabric that binds it all. Stay curious, because the adventure has only just begun.